Welcome to the video on plane and line intersections. So first we'll learn about intersections between a line and a plane. So it would be something like this. You'd have a plane and then a line that goes through the plane. So we want to find that point where the line hits the plane. So a line and a plane intersect at a point. Unless the line is on the plane, then the entire line would be the intersection. So to find this intersection point, you would find the parametric equation for the line. So your x equals something t plus 5 or whatever, and then your y equals and z equals. And then you'll plug these values into your plane equation. So your plane equation would be ax plus by plus cz equals d. So you would plug this in for x, you would plug your y value in for y, and then your z value in for z. So by doing that, you could solve for your parameter here. Once you've solved for your parameter, then you could plug that in. So if we found that t equals 3, for example, then we could go back and plug in 3 here, and x would be 3 plus 5, which would be 8. And then we could find our y and z values as well because we'd know our parameter t. So that's how you find where your line and plane intersect. Now we have intersections of multiple planes. So if we had two planes, then they would intersect at some line. It's kind of hard to picture because it has to be in 3D, but they would intersect at a line. So to find the intersection, you need to find the normal vectors for the two planes. And once you've found these vectors, so you would have a normal vector that would point straight out from this plane, and another normal vector that would point straight out from this plane. So you could find the direction of your line by taking the cross product of those normal vectors. Finally, you would find a point on the line by setting one variable equal to 0. So you would have two planes, so you'd have ax plus by plus cz equals d, and then another ax plus by plus cz equals d. So if you set one variable, like z equal to 0, then that would go away, and you would have two variables, your x and your y. So then you could solve for x and y by using substitution or elimination, and then you would have x and y when z is 0. So you would have a position vector, and then you could write the equation of your line using your position vector found from this step, plus your parameter times your direction vector, which you had found. So that's how you would find that intersection line. Finally, with three planes, they'll intersect at a point, and to find that point, you would find where the two planes intersect, that line like we found in the previous one, and then you'll find where that line intersects the other plane, like we did on the previous slide. So that's how you would find your intersections. We'll do practice with this later. Next is angles. So first we're talking about finding the angle between a line and a plane. So you've got some plane, and then some line that will go through the plane. And we're trying to find the angle between the plane and the line. So if we imagined looking at the side, it would look something like this. So you'd have this line here, and then this plane would go in and out more this way. So we want to find the angle here between your plane and your line. So to do this, you'll find the normal vector for the plane, which would point out this way, and then the direction vector for your line, which would point this way. And then you'll use your equation to solve for theta to find the angle between them. So if I draw the side view of the line and plane again, this would be our plane, this would be our line. Our normal vector will go 90 degrees from the plane, and our direction vector is going this way. So our angle would be this angle here. But we want to know the angle between the plane and the line. So that would be this value here, alpha. So to find the angle between the line and the plane, you'll then take 90 degrees minus that theta value. Or if you're doing it in radians, you would do pi over 2 minus theta. To find the angle between two planes, you would find the normal vectors. So we'll do a side view of both planes. So we've got plane 1 and plane 2. Our normal vectors would go like this and this. So we'd find the angle in between, which is this, which would be equal to the angle between the planes. Or you could do 180 degrees minus that angle to find your bigger angle between them. And you could do that same thing in radians, pi minus theta. So that's how you would find angles. So now we have our first IB practice question, which is no calculator. It says find the intersection of the following planes. So we have plane 1, plane 2, and plane 3. So the first thing we want to do is find the intersection of plane 1 and 2. So to do that, we'll find both of our normal vectors. These are in Cartesian, so it'll be easy to find our normal vectors. So for plane 1, the normal vector is 2, 3, 1. And for plane 2, our normal vector would be 1, -2, 4. So we're trying to find the line where they intersect. So to get our direction vector, we'll take the cross product of these two normal vectors. So we'll have I, J, and K, and 2, 3, 1, 1, -2, 4. So this is equal to I times, if you cover your row and column with I, then we're left with 3, 1, -2, 4. Then we have minus J times, if we cover our row and column with J, then we're left with 2, 1, 1, 4. And then plus K times our determinant. If you cover your row and column with K, then you'll be left with 2, 3, 1, -2. So we'll have I times 3 times 4 is 12 minus 1 times -2 is -2. So this will become plus 2 minus J times 2 times 4 is 8 minus 1 times 1 is 1 plus K times 2 times -2 is -4 minus 3 times 1 is 3. So we have 14I minus 7J minus 7K. So our direction vector is 14, -7, -7. So this is the direction. Now we need a position vector. So to do that, we're going to plug in 0 for z in both equations. So we have 2x plus 3y plus 0 equals 4. And then x minus 2y plus 0 equals 18. So if we solve this second equation for x, we'd get that x equals 18 plus 2y. And we can plug that in for x in our first equation. So we'll use substitution. So we have 2 times 18 plus 2y plus 3y equals 4. So 36 plus 4y plus 3y equals 4. If we subtract 36 from both sides, we'll get that 7y equals -32. So y equals -32 over 7. We can now find x by plugging in y. So x equals 18 plus 2y. So 18 plus 2 times -32 over 7. So x equals 18 over 7 is going to be equal to 126 over 7. And then we'll have minus because it's a -32. So 2 times 32 is 64 over 7. 126 minus 64 is 62. So we'll have 62 over 7. So for our position vector, we have x is 62 over 7 y is negative 32 over 7, and z is 0. So we can write our equation of our line as r equals our position, so 62 over 7, negative 32 over 7, 0, plus a parameter, we can say t, times our direction vector, 14, negative 7, negative 7. So in order to find where our line intersects our plane, that'll be our second step. So intersection of plane 3 and our line, we need to rewrite our line in parametric form. So x is going to equal our 62 over 7 plus 14t. Y will equal negative 32 over 7 minus 7t. And z will equal just a negative 7t. So we'll plug these into plane 3. So we have negative 3 times x, which is 62 over 7 plus 14t, minus y, which is negative 32 over 7 minus 7t, plus 8 times z, which is negative 7t. And all that has to equal 1. So negative 3 times 62 over 7 would be negative 186 over 7 plus 14 times negative 3 is going to be a negative 42t. Then we have minus negative 32 over 7, so that'll be plus 32 over 7, minus negative 7t, so plus 7t. And then we have minus 56t equals 1. Negative 186 over 7 plus 32 over 7 is negative 154 over 7, which can be simplified to negative 22 over 1. And then we'll combine our t's as well. So we have negative 42t plus 7t minus 56t. So we have minus 91t, and that equals 1. So we'll add 22 to each side. So we have negative 91t equals 23. So t equals negative 23 over 91. So now that we've solved for t, we can plug that in to our parametric equations here to find our x, y, and z coordinates. So x equals 62 over 7 plus 14 times t, which is negative 23 over 91. So that equals 484 over 91. Then we have y equals negative 32 over 7 minus 7 times t, so negative 23 over 91. And that equals negative 255 over 91. And finally, z equals negative 7 times t. 7 and 91 simplify to 1 and 13. So this equals 23 over 13. So the intersection of the three planes would be at the point 484 over 91, negative 255 over 91, and 23 over 13. So most likely on your test, they won't give you fractions like this on your no calculator portion, but this is just an example to show you a more challenging version of the problem. Now for our second IB practice question, it says find the angle between a line with an equation x equals 2t minus 1, y equals negative t plus 3, z equals 3t minus 4, and a plane with the equation 5x plus 2y minus 3z equals 16. So we'll have a plane and a line. So this plane would extend in both directions. So we want to start by finding the normal vector to our plane. So our normal vector is easy to find here because it's given in Cartesian. So our normal vector is going to be 5, 2, negative 3. So we want to find the angle between our plane with this vector and then our line with its direction vector. So the direction vector is going to be the slopes. So 2, -1, 3. So to find an angle between, we'll use our v dot w equals the magnitude of v times the magnitude of w times the cosine of theta, and we'll solve for theta. So we have 5, 2, -3 dot 2, -1, 3 equals the square root of 5 squared plus 2 squared plus -3 squared times the square root of 2 squared plus -1 squared plus 3 squared times our cosine of theta. So 5 times 2 is 10, 2 times 1 is -2, and -3 times 3 is -9. So that equals the square root of 25 plus 4 plus 9 times the square root of 4 plus 1 plus 9 times our cosine of theta. 10 minus 2 is 8, minus 9 is -1. So -1 equals the square root of 25 plus 4 plus 9, so 38, times the square root of 4 plus 1 plus 9, so 14, times our cosine of theta. 38 times 14 is 532, so we'll divide by the square root of 532. So we get our cosine of theta equals -1 over the square root of 532. So our theta equals the inverse cosine of -1 over the square root of 532. So if we plug that into the calculator, we get that theta is approximately 92.48 degrees. So we solved for theta, and we solved for our angle that's greater than 90 degrees. So this is theta. So we need to subtract 90 from that to figure out our actual angle between them. Or we could do 90 minus 92.48, which gives us -2.48. But we could just switch that to positive because our angle is just going to be a positive angle. So 2.48 degrees is the angle between the plane and the line. So in summary, a line and a plane intersect at a point unless the line is on the plane. To find that point, you'll plug in parametric equation values for x, y, and z in the plane equation to solve for the parameter t, and then plug in the t value into the parametric equations to find the point. Two planes intersect at a line. To find that line, you'll find the normal vectors of the plane, then find the direction vector for your line, and find a point using substitution or elimination, and use the direction vector and the point to write the equation of the line. Three planes will intersect at a point. To find that point, you'll find where the two planes intersect, and then find where that line intersects the other plane. To find the angle between a line and a plane, you'll find the normal vectors, and then find 90 degrees minus the angle between them. Finally, to find the angle between two planes, you'll find the normal vectors, and then find the angle between them. That's all for this video. Thank you for watching.